And Windows internals is something I've taught many times from many angles. I did Microsoft Windows tech support for a while, and then malware analysis, exploit development, and now instant response. They all have a lot of Windows internals in them, and forensics. Understanding how Windows works is just really important, and whatever part of computer security you study, you are going to get back sooner or later to having to learn a lot about how Windows works, because Windows is a big part of it. And so our interest here is from the malware analysis side, but then basically you have to understand the Windows API. So the API is the application programming interface. This is a general term for a platform that lets somebody else use some of their services, like Facebook is a platform. They are not a product, they are a platform, and they encourage other people to write games and quizzes and surveys and stuff that go on Facebook, and they make it easy for third-party people to make something that runs on Facebook, so more people will go to Facebook and enjoy it and have fun and make all their friends join and see more ads and make money. That's how they make money. And Microsoft is the same. They want to make a platform so you can do things in it. And that's what the API is. The API is, you have the internal workings of your product, which are for only your developers, and then the API is the public side, the functions you allow other people to use. Like Google lets you use Gmail, but they don't let you go into their main database and change the stuff they're searching for or anything like that. That's private. So they have some things that are provided to the public in the API and other things aren't. So that's the game here. So here's some fundamental concepts of how it works. They call this thing Hungarian notation, this way of naming things. And they're all basically C. Everything is written in C, or I think these days C# or C++. But you have these DW for 32-bit words, W for 16-bit words, handles and long pointers. And these are prefixes before an API data variable, so you know what it is. And then you have handles. Now, handles are how C works. If you want to write to a file, you do file open, and C returns a handle, which is a pointer to an object. And the same thing, everything you do in C is manipulated with handles and pointers. So the handle is the sort of a name you use to refer to it, and all you can do is store it and use it in a later function. So create windows is one of Microsoft's API calls. They always have this pattern of words rammed together, capital letters on the words, and often EX or A or W at the end, indicating that it's been extended because it was in some earlier version of Windows and was later changed, or that it uses 8-bit characters for A for ASCII, or 16-bit characters, W for wide characters. And so you would call a create window function, and it will return a handle to the window. And now when you want to do something else like minimize the window or close the window, then you will refer to that handle so it knows which window you're referring to. The same way in old-fashioned C, you would open a file, get a file handle, and then you would read using the file handle, write using the file handle, and close using the file handle.
And a file handle is just a memory address.
Yeah, it's apparently somewhat different than a pointer, but it acts basically the same as a pointer.
But it's just literally just a memory address.
Apparently it's something a little more complicated than memory address. I don't know quite what it is, but it's used to refer to that object. So create file will create a file, read file, write file. You can create a file mapping, and so on. These will load files into RAM, which is not something normal people want to do as much as malware people want to do it all the time. This is one simple antivirus evasion technique, one of the ones I found in the Violent Python book that worked against a whole bunch of antivirus engines a few years ago when I tried it, was to have a program that had a data section and then copy it into RAM and run it. And the scanner doesn't think it's executable, so it doesn't care. And once it's in RAM, it's no longer scanned, and you can sneak malware past antivirus that way. So there are special files for this. Shared files on Windows systems are done with \\/ server name \/ share name. That's their convention. And that's a general of this double / thing is part of a general namespace. The \ here is the equivalent of Unix / the root of everything. And this is the device namespace \/ dot / that you use for direct I/O. It's the same thing in Linux. You have /, and then you have things like /SDA, which is the physical hard drive, and then you have /SDA1 and 2 and 3, which are the partitions on the hard drive, which are the equivalent of Microsoft drive letters C, D, and E, because the drive letters refer to a part of a drive with a name for storing files, but the raw root of the drive itself contains other things, like the master file table and such, which we'll be talking about later on. So that's the game there. You can write to \\, dot / physical disk 1, and now you're writing to the direct hard drive, which is not something you normally do, and you can corrupt the disk so it won't boot anymore and the volume information is lost and all that jazz. Something you'd only do this if you're trying to forensically wipe the disk, or if you're trying to low-level format the disk. Not something you should normally be doing from inside any program that's supposed to be reading or writing files. You can have alternate data streams. These have been around for a long time. They were originally made as part of an Apple file format to store the cover art and album lining for songs. So you'd have the playable WAV file or whatever it was, and then you'd have the art and the liner. So you'd have multiple streams of data tied to one file. And you can do it on Windows. You can take a file, and I can make a 5 million foo with 1 byte in it, and then I can send more data to foo:\bar.txt. So you put the file name and you put a colon there as if it was a drive, and you store more data in it with another name, and it puts a second stream of data on the file. And it still thinks the file is only 4 bytes big. It's lying because the dir function only sees the main stream. It's a pretty good place to hide things, and there was a time back in the days of Windows XP when this would fool everything, like antivirus products, and you could hide executables in there, and now all your antivirus and forensic tools know to look here for it. And then there's the registry. Back in the days of MS-DOS, Microsoft used text files to contain configuration information for the operating system and utilities. Linux still does. So if you download Apache, it's got httpd.conf and apache.conf and all this jazz. And if you put it on a different kind of Linux, it has similar configuration files. And if you download something else, every utility, the people who write a utility also write the configuration files, and they put them wherever they want. So you just have to read the documentation for each utility and hunt around to find them. And that is the way Microsoft used to do it, but they decided they didn't like that, and they put it all in a binary tree structured registry, which has all the configuration for all the Windows settings and all the installed applications here. This is why you always have to install Windows software, but on Linux you don't really have to. You don't really care, usually it's in the program menu or anything. Although these days we install quite a few things. But anyway, and there are people like Rusinovich at sysinternals that make Windows utilities you don't have to install. You just unzip them and run them. He never got involved in this messing with the registry or anything. They're not registered anywhere. You just run them by going into that folder and running it. That's the old-fashioned technique. And you can do things that way, but most of the time they now put it in they make a bunch of registry entries associated with it. So this is where all your settings are. And malware uses the registry for plenty of things, but the most common thing is persistence. The registry is where a lot of the auto start extensibility points are. You can see them if you get the Autoruns tool from sysinternals. There are about 30 ways to make programs automatically launch when you reboot in Windows. And many of them are registry keys. So the registry looks like this. It is structured with 5 root keys. These are pretty screwy. They do not map to 5 files. They map in a very strange way to hard drive and disk. Some of them aren't on the disk at all. Some of them are actually contained, like the current config is actually contained inside one of the others. It's very strange. It's not at all like 5 folders on the hard drive, but it looks like 5 folders. Those are the roots, and then you have these long paths leading to things. You can edit it with regedit. You can output it as reg files, and so on. Here's generally what they are: settings for the local machine and the current user. This is information defining types like file type, associated things to open, file extensions. Here's the current hardware configuration. So not all the data here was ever stored on the disk. This was formed during post. When it was probing your hardware to see what you have, it decided what to put in here. And HKey users defines keys specific to each user. And anyway, the run key is one place. Microsoft Windows current version run. Everything here will automatically run when you restart the machine. And there's a run once, and there's a whole bunch of related run keys. And this is one of the commonest places to put a auto start entry to start malware. So like I say, Autoruns is the best tool for this, written by Mark Rusinovich, who is fantastic at sysinternals. He's very, very good at finding what's going on inside Windows. And his tools are great. And he has the best tool to find all the stuff. It is kind of nuts. You would think there would be one way to start something. Of course, Linux is a simple mess. You have the init.d, then you have systemd, then you have all these files, you have all these run levels, you have a bunch of login things that happen. It's the same way. There's many, many ways to automatically launch something. And the bad guys, of course, hunt up the most obscure one, so it's hard to find their restarting stuff. This is what Autoruns looks like on a machine I ran it on. So it's got Adobe ARM, Dropbox, LogMeIn, some sound in Java, and all this jazz. All these various things are on there. And notice all the tabs. All the things that automatically run when Windows launches. You know, if you start Windows and go into Task Manager, there's about 75 processes running. You can find out what they all are, why they all start, and it's the same on Linux. Just type PS and you'll see a pile of junk running, and there are whole books on the boot up process. It's fantastically complicated and pretty interesting too. Anyway, then you got registry functions. These are the API calls you use to open a key, set values, get values, and so on. And I mentioned before, the documentation will often not bother with the W or A. They just expect you to know that doesn't really matter. There's the convention for all this, X, A, and W, explaining it, but I've given you a quick summary of it. So here's code from malware that will do this. It will call open the key here, then it will call some other function here that does string length, then push something, load effective address of something, load the effective address of that and push it. Now this is all how function calls are. You're pushing a bunch of junk on the stack with all these pushes. Those are all the parameters for one of these API calls. And eventually at the end there will be, and that's it, the reg set value. It's off my screen a little. Reg set value is going to set a value, and all of those parameters are the path to the value, what type it is, what data to put in the value, and all that junk is the assembly language required for one function call, which would be one line of C or C++. You can save these things in reg files that are just plain text. You can just export them from here, and then they're just plain text. You can open it in Notepad that just set these things for you. It's one simple way to export registry keys. I've done this for things like Microsoft has an update we don't want, and there's a registry adjustment made to not take the update, and so you make a reg file, stick it in a USB drive, and get people to run it. It's far better than asking end users to go and regedit and mess with it. Never do that. Regedit is really dangerous. If you go in here and accidentally drag things around and drop them and change permissions, your machine is destroyed. So you never send users in here. You give them a reg file to double click on. Yeah.
So is there a way to read the text registry file into config the system?
A way to read a registry file into what?
Read the registry file so you can automatically update the computer.
So you get what? The updates?
Yeah, but if you get the registry file and then put it in a text file and then you modify it and you want to read it back to.
Yes, you can do that. When you can run a reg file and that will put those modifications in. And you could even modify it in Notepad and then run it. That would be one way to do it.
When you run it so we can.
When you run it, it'll put those changes back in the registry.
So you run it, you're not going to do it in the register, right?
No, you just double click it. Yeah, and the default action is to run it with the command line reg command, which puts those things back in.
So you take the text edit, export, make the changes.
You could.
Just save it as a .reg. And,
Yes.
And then you double click it and it'll execute it.
Yes.
Okay.
You can totally do that. That works. Yep. All right. Yes, so save this thing, export the registry file, and then you've got a registry file that looks like that, which you can see it's quite readable. You just have these long registry keys and values, and you could just edit it here, and then when you double click it, it'll put that stuff in the registry. Of course, you need administrator rights to do that, which is a good thing because you don't want amateurs messing with the registries. All right, so we got some iClickers. I better start Zoom for the remote attendees. So, which one is a pointer to an object, or something close to that? That's the handle. All right. Which one is a second stream of data in a file? Okay, alternate data stream. Which one of these is a root key? That's the first one, good. All right. Which one is from sysinternals? All right, that's Autoruns. All right. And which one's a pointer to an object?
Can we do this?
Sounds like a duplicate. Is that a duplicate? It is a duplicate. Well, that's life.
We should all
wrote
get it
these?
correct.
What's that?
We should all get it correct.
That's one possibility. I've often found that even when one gives you the answer to the next one, a bunch of people still don't get it correct. You know,
Same. They just look half an error.
There's,
Wait, what?
yeah, that'll happen. It's not like you think. So then there's networking, API calls, application programming interface. This all started with Unix. The internet is a Unix production. The whole point of it was, in the early days when I started this back in the 80s, there were mainframes. VAX had one, pile of manuals, IBM had one. They all had different operating systems. You had to learn it. It was specific to one brand of computer, and that rapidly seemed stupid, so they wrote Unix to unify it all. And then they wrote C to be the language Unix was written in, and now all you had to do was write a C compiler for each brand of hardware, and everybody could compile Unix, and now Unix was the unified operating system. And once that was done, you could now have the internet because the machines at the end were all compatible. And so they invented the Berkeley standard sockets with the BSD Unix, Berkeley standard, one of the canonical branch of, versions of Unix, the branches. And this has the standard way to make networking, and Windows was nowhere. Microsoft couldn't care less. They only cared about local networks, and Apple was the same because they said there was no internet that mattered for most people. They just wanted to have small networks you could share the printer in your office. And they used stupid things like Apple Talk and NetBIOS that would never scale to the internet, but were just useful on a small local network. And by the time they came to the internet had already been developed and was running, and it was Unix production, and all they had to do was import that code and use it. So you have these functions, which we use a lot if you take my 124 and we do Python. You may create a socket, you bind and listen and accept, then you connect to some other server, you send and receive to that connection. These are the raw socket operations that do raw networking. Most developers do not do it this way. They use higher level methods, but this is the raw socket library that does it all. That's where you make every connection. That's the game here. So if you're going to do this, you have to start with WSA startup, and then you can use these libraries, and they're in the WS2_32.dll. These are the low-level WinSock libraries, and you may remember something called 2 Cows on the Internet, the ultimate collection of WinSock software. There's a whole bunch of software that uses this stuff, which I imagine is because it was all ported from Unix. I'm just guessing, but that would seem like the logical reason why you would rather have written this way. Anyway, so on the server side, you open socket to create a socket, then you bind to a port, then you listen, then you accept data. On the client side, you make a socket, and then you connect to the server, and then you send and receive. So here's a simple server program. You would call WSA startup to prepare these libraries for use, then you'd call socket to define a socket object, then you would call bind to connect a port to it on a local machine, and now you listen on that port, and then you accept data. And this is a simplified program. You would never really do it this way. This is the way I would do it in like my violent Python, because we're sleazy attackers, but real programmers don't get to write this. Every time they do anything, they then have to say, what if an error happens, do this, do this, do this. So everything is 10 times longer and really boring, because after everything you do, you handle all the errors. Then you do one more thing and handle all the errors. If you don't do that, of course, it's useless because it crashes all the time. But if you're an evil attacker, that's okay. So the WinlNet API is higher level. This is what a normal program would actually use. This has things like Internet Open, Internet Read File, Internet Open URL, so you don't even do the handshake or anything. And this is really good because you might want to use a modern protocol like HTTPS. And figuring out how to do the encryption and the key back here is going to make you cry. So you use some routine, something like this, that will do it all for you. Anyway, so to follow your malware, jump and call, move code to another place. That's the simple way to do it, but there's a bunch of other ways to do it. And we're going to talk about these. These are intended for special purposes, and malware will of course use them just to make it more complicated to baffle you. So DLLs are the fundamental way almost all malware runs, because Microsoft uses dynamic linking. So you can be running a program, and the program can say, oh, you want to do something, I don't have any code to do that. I'll load another library right now and connect to it, and then I can do that. And it doesn't have any way to know that that's a genuine library or anything. There's no signatures or anything, so you can totally just make it load the fake library full of junk, and it will run it. So that's the game. So DLLs are executable files that export functions. Exports are named ways to enter your code. A normal function has only one export, which is start or main to go in, but libraries have hundreds of them, because I could do this, I could do that, I could do that. I contain all these functions you can use, many exports. So DLLs, of course, are used in Windows because they make programs load faster, they make them lose less RAM, they make them run on cheaper hardware, and they facilitate people that want to sell their software, because you can write a library and then sell it to 100 people that will use it in different applications. So there's on Android, I see this all the time. There's something called Bouncy Castle, and there's 3 or 4 crypto libraries, and every Android app uses 1 or 3 or 4 main libraries. They just license the code and put it in their stuff, and everybody uses the same modules, which is true on the Unix side too. This is why something happens like OpenSSL, or what was it? What was the Heartbleed? Was it OpenSSL? Had a vulnerability, and turned out like almost all Unix code in the whole world was vulnerable because everybody just uses the same library, which is, by the way, the right thing to do. Don't write your own crypto, you'll really be sorry. But it does have this supply chain issue, just like that scare about the chips. You're all trusting the supply chain, and then you can ask, who actually audited the supply chain? Who would we sue? And they said, well, some drunk in Finland changed it at Christmas and nobody looked at it for the next 2 years. This is why people say, why don't we buy software from a company that we could sue, where they would therefore have some motivation to actually audit it and stuff. Anyway, that whole open source philosophy always sounded kind of bogus to me, but I'm an evil capitalist. The idea of people actually making money and that motivating them makes sense to me. And anyway, so you can put malicious code in the DIL, or you can use the existing DILs to do bad things, and you can even use third-party DILs. Like you could use the Firefox DIL to do your networking, because just assume they have Firefox installed in the box, because a lot of people do. That would be a way to dodge things that are looking for your use of the Windows API. So like say, DILs are a portable executable file format, and they have to have a flag in the header that tells them it's a DIL, and then they have many exports. They have one function called DIL main. Remember that one function, WSA admin, had to be run first. This is the same kind of thing. That's the one that prepares the DILs for use. So when you load a DIL, it automatically runs DIL main, which is the setup routine. So if it's a malicious DIL, you just put the malware in DIL main. And now as soon as they load it, it runs your malware. So everything you run on Windows is running in a process, and each process has its own virtual address space. They actually cannot reach into another process's memory. They all think they're running at the same address, 400,000, at least the EXEs. And you see them all running. You open Task Manager, you'll see dozens of processes on every Windows machine all the time. This one here had 50 processes. And so each process has its own memory region, and if 2 processes access the same memory address, they're actually accessing their own separate copy of that memory address. They're not, that's the virtual address space. They each think they're running at 400,000, but they each have their own little spot, which is in fact randomized on modern systems. So you can create a process with create process, and then you have a parameter to pass in all this information, like what it's going to connect to for input and output and all that jazz, or connecting it to a socket, creating a remote shell. And this is, of course, the Windows component object model. You can write code, which was originally a function, in one application, and you can then make it a service and share it with every application on the machine, and you can then connect it to the network and share it with everybody in the world. And the original developer probably didn't know you're ever going to do that or understand the security consequences, and this does lead to Microsoft's endless chain of security vulnerabilities, because code is reused in a larger context. This is, of course, the way to make a lot of money. You have your little show, and then you take it on Broadway, and the whole world sees it, but you may or may not really be ready for the big stage. Anyway, so here's code to create a shell. I load various bits of information up here at locations calculated from ESP. This is one way to put them on the stack. And then I'm going to put a command line command up there, and a socket handle and all that jazz, and then I'm ultimately going to call create process. So I just prepare it with a command line and all the other properties, and then create the process. The processes are just containers for threads. The only thing that actually gets any CPU cycles is a thread. And so the threads are independent sequences of instructions that can proceed while the other thread is waiting to make it more efficient. And each thread has its own registers and stack. And when one thread has gotten all the share of CPU it deserves right now, it has to store where it left off and switch to the other thread. And that is called a context switch. And that's the thread context. It has to store the context and move to another. All right, so create thread. This will create a thread, and you can load a malicious DIL into a process. And you can make mutexes. Now, mutexes are how you do have inter-process communication. So it lets you have one process put a signal in memory which can be read by the other process, so now they can talk to each other. If you do it in user land, it's a mutex. If you do it in the kernel, it's a mutant. And these things are simple handles for interprocess communication for things like record locking, and the malware typically creates them to mark this box as infected so that it won't try to reinfect the same box again. So you can wait for a single object. This will give a thread access to the mutex. This is one thing, since the mutex is shared by multiple threads, you have to lock it. You have to wait for your turn and say, nobody else can use it while I'm using it. I'm used to this from World of Databases where I started long ago. You'd have to lock a record, otherwise two people will modify the same record at the same time, creating a mess. When one person's modifying it, it's locked. Everybody else gets an error message. They can't get at it until I'm done with it. You can release it and create mutex and open it and all that jazz to connect to these mutexes. So here's one, just the one I described. This is going to open a mutex looking for this thing called HGL 345. So the debugger here, or disassembler, will tell you that this offset points to that string to help you. So you put that on the stack, then you call this create mutex, and it'll create a mutex with that name. So now if somebody runs another copy of the malware, it will see that mutex and know not to try reinfecting the box. All right, that's the one, bind and accept. Where's that? WS232, the WinSock library. Where's Internet Read File? The one with a friendlier name, WinINet. All right, this thing is like an exe, but only one flag is different. All right, that's a DIL. All right, and a global object used to coordinate multiple processes. All right, that's much better, a mutex. Let me make a note. Totally different set of winners. All right, so services are these things that run in the background, and the point of them is they are not providing something that a user wants. They are providing a service that a program will use. So they just run there without users connecting to them directly, and your programs call them. They run as the system account, which is what starts the machine before you log in, and most of them continue to run with system privileges because they've started from before you log in, and therefore, malware that can start as a service can start with high privileges and get persistence, typically. So you do these things with the API calls to open SC Manager, create service, start service, and so on, the usual stuff. You can have a whole bunch of services. See, this is the way Microsoft is. It's easy to get a bad attitude about Microsoft. Like all big companies, they do a lot of things that are kind of sleazy when inspected. Like right now, Google is working on a secret thing to write another censored search engine to distribute in China like they did in 2010 to get back in the Chinese market. There's 1 billion people there. You just can't resist. A gigantic customer base. How can we possibly justify not being there? You can't really. You can say, we're too moral to go to China, but every year you say, there's 1 billion users there. How moral are we again? And there's all these arguments that we'd better to go there. There's lots of arguments. There's 1 billion arguments. Anyway, so so now they're going to make a secret version, and it's the same thing, So one of the things Microsoft did was people complained it took too long for Windows to boot up. So they invented this delayed service so that Windows XP would give you the start button really soon. Nothing worked, but the desktop and start button would appear fast. It delayed the rest of it, not to happen until later. So it looked like it was up. The internet didn't come up till much later. But anyway, so that's the game here.
Do that with apps. I would launch the image that looks like the app.
Yeah, there you go.
It doesn't work.
Yeah, but at least then people don't complain so much.
Yeah, but people are going to still look at it, and they still don't know what they're going to push.
Yeah, that's right. And and you can say this is dishonest, but it's just serving people. It's giving them what they need. Like the TSA doesn't actually stop the guns from getting on the plane. They stop the people from feeling so scared to get on the plane. They get the people on the plane by making them think somebody hunted for the guns. And that does prop up the airline industry, and otherwise it would go broke. So it's, there's a lot of cases where being dishonest in business is the right move. And this is why Google got big enough, they had to take away their plan to not be evil. Because once you're big enough, good and evil just are hard to figure out anymore. Especially once people invest in your company. If people invest in your company, that's their retirement fund. So doing an evil thing to make more money is a good thing.
So you're saying too big to be good?
Well, yeah, once you're big enough, every move you make hurts somebody. Anyway, so
I had a question. So the services support kernel mode, user mode?
Either way. Either way,
So
either
just-
kernel mode or user mode. Yeah, some services run in the kernel, some, yes, exactly. All right, so the share process is the most common one used by malware. This is where you have many services provided by one process, all running as SVC host. And if you run sysinternal's tool here, Process Explorer, you will see all these SVC hosts running. And if you hover over it, it'll tell you this one is running the window manager and the network connections manager and program compatibility assistant. Each one of them is running 5 or 6 or 10 things. So your malware can just add itself to one of these lists in the registry and it will launch with one of them. All right, there's other ones. You can run an EXE as an independent process, and there are kernel drivers. These are the ones that run with kernel privileges, loading a kernel driver, which will then run in ring 0. So here's the service information in the registry. This is where you have all the different types of services here, and each one of them will have their setup here. So you have a description. This is the browser service. Here's the display name. Here's the path to it. It runs as Svchost.exe knet svcs. That is the particular service run within an SVCS process, which might be running 10 other things at the same time. And all you have to do is make a registry entry like that and point to your executable, and it will load your executable on boot up with system privileges and run it there for you. SC is the command line tool you can use to do this. You can control services, view them, and disable them. And as Kirk figured out last week, you can get rid of Windows Update on Windows 10 by using SC carefully and killing the Windows Update service, which is very handy because the Windows 10 updates are horrible and you want to block them. And Microsoft doesn't want you blocking them, so they don't give you an easy way to block them. So the component object model is part of Microsoft's system that makes it easy to share code. So you can use the component object model, and then you call OLE initialize for object linking and embedding, or co-initialize, and then you can call these COM libraries, and you can refer to objects by these GUID numbers. And these are 128-bit addresses like IP version 6. Microsoft calls them globally unique identifiers, and it's the same on every system because they're not globally unique. Whenever Microsoft has a name, it always means the opposite of what it says. And so the different class identifiers and interface identifiers, these are just various ways to refer to shared code in libraries, or else
It's unique within that system.
it is unique within that system. It's a
Yes.
unique identifier. That's why there was one that came out a few years ago. People said God mode. You could type this long string in, then you get basically control panel. They said it's the secret hidden way to control everything in XP. They said, well, you know, it's really nothing more than control panel, but you can open it in a different way. You can open every part of Windows by just typing in the GUID. Run this. You can refer to the base of computer, and everything has a GUID. But it's not, you don't normally do it that way, but it is internally what you use to refer to Microsoft objects. So then there are exceptions. We've talked about error handling before, how that assembly language we were looking at was not professional. It would have had a whole bunch of error handling. And Microsoft, of course, has a ton of error handling too, or the thing would crash and die even more than it does. So if you write code, you can write your own error handling routine in the code to handle really serious errors like illegal instructions, attempts to divide by 0, attempts to access memory outside your range of acceptable memory, and then you put that code, pointers to those functions, in the structured exception handler, which runs a series of routines trying to handle those exceptions. And they're stored in the segment register. FS0 tells you where the SEH is, and we play with it in the exploit development class. And you have a chance to have as many handlers as you want to handle exceptions, and if all of them fail, it will dump back to the operating system, which will then do something like pop up a box saying this program has crashed. Would you like to query some Microsoft help desk and get no useful information? So the kernel, this is the hardware layout of the motherboard and the processor. The earliest processors would just have an instruction set like the 6502, and that was it. Everybody could execute the instructions. But the Intel moved up to the higher security model where there are certain instructions that are considered dangerous and others that are considered less dangerous. So ring 0 is the ones that directly send data out to the devices, and that is considered dangerous. And ring 3 is the less dangerous instructions. So user land programs live in ring 3. Ring 2 and 1 are never used by any modern operating system, for better or worse. And ring 0 is kernel mode. Kernel mode is a small heart of the operating system. It's loaded during boot up. It always stays in RAM, and you never directly use any kernel mode routines. You live in user land where everything you launch goes, everything that's a child of Explorer. After you've logged with your name, you don't have the privileges to run any kernel routines. All you can do is ask kernel functions to do things for you. And Microsoft provides you with some of them. And unfortunately, everybody that writes a device driver has to load it in the kernel, which is very, very annoying to Microsoft and all the rest of us, because Microsoft tries to write good code, and when you buy a cheap, lousy NIC or a printer, they give you some crappy driver, and you load it, and it puts junk in the kernel and causes the blue screen of death, which really, really irritates Microsoft, because then people complain to Microsoft, and it's really not their fault. But that's the way it is. So user mode is where almost everything runs. All the applications, your desktop, everything from the start button and all that jazz. And it can only reach the hardware by going through the Windows API. So each process has its own memory. Now the point of this is those processes are not touching the heart of the operating system. So if a user mode process crashes, the machine is still working. The kernel is still okay, so it can pop up a box and say, this program crashed, would you like to restart or something? It doesn't have to just die. If the kernel crashes, you get the blue screen of death that says, I'm dead, I give up, I can't stand life anymore. And it doesn't even have enough energy to give you an error message that'll help you. It says, I give up, you're horrible. And that's the game. So you get into the kernel with sysenter, syscall, or int2e are the assembly language instructions that bring you in. And then it goes to lookup tables that call for kernel routines. The kernel routines all share processes, and something, I did a DEF CON presentation and a lot of videos a few years back with an IP version 6 attack. All you have to do is burden the kernel with too many IP version 6 address requests, and you'll get the blue screen of death. And I couldn't understand how this could be, and the kernel experts told me the kernel has no memory management. You launch processes and it doesn't know if it has enough memory to run it. And if you make it do too much, it will just die. And I said, you gotta be kidding. I said, oh no, it would slow it down too much if it actually checked to see how much resource was available for launching a process. It just launches them. I said, no, that can't be right. And apparently that is really right. And because I found out the same thing about, I think it's Android phones and iPhones. They will just launch an app and then they'll crash. Sorry, not enough memory. I wasn't able to check before launching my app that there wasn't enough memory available. I say, how can that be? But it is true, apparently. Anyway, that's the game here. So if anything bad happens in the kernel, you're dead. Blue screen of death. And your firewall, your antivirus, and your device drivers all run in kernel mode. So if you have sleazy companies writing those things, they really mess up your machine. Anyway, so you can put malware in kernel mode. That's where the rootkits typically live, because then they're really hard to detect and remove. And that's the game there. Most malware does not run kernel mode. Things like keyloggers, it's just the kernel mode rootkits that do, and those are the nastiest things where you usually can't clean them off at all, and you just have to reformat your machine and reinstall Windows.
What is auditing does not apply to kernel?
Auditing is a service that Microsoft has that puts entries in the log whenever you do things like access a folder or launch a process. You can turn on auditing, but it doesn't apply to kernel processes just because the kernel has low overhead. So it doesn't bother doing extra things, which would be nice. Yeah, anyway, so then there's the native API, which is good, clean fun. So like I mentioned before, there's the internal code that you aren't supposed to use, and then there's the public code you give people at the API. Well, the inside Microsoft, they have the secret API, which is not documented, which of course has all the goods. And so nt.dil is the native API. You can directly call stuff in nt.dil. You are not supposed to do that. It's not documented, and you aren't supposed to know what's there. Although, this is 126, right? In this class, I think we are going to actually play with this, and you'll see it. If you go into WinDebug, you can debug the kernel, and you can totally see this stuff. That's why you don't need a secret deep throat in Microsoft to leak it out. It's actually pretty easy to read this stuff and see how it works. It's not very well hidden. So you can use these directly, but you're not supposed to. You're supposed to use kernel 32, which is like that WinlNet library. It gives you a high function. It's supposed to call ntdil and NTOS kernel to get into the kernel. So what you do, yeah.
Is syscall inside one of these?
Oh, syscall is what's used to do this. So you wouldn't normally do it. You'd call this, syscall is what it's actually going to use to do that. But normally you would just call ntdil, which would do a syscall on your behalf. And so the native API is of course more powerful. All the really good stuff is in there. And so what happens is typically your security programs like antivirus catch the calls to kernel 32, so your malware can just call right into the hidden API and do stuff, and your antivirus doesn't get a chance to catch it. That's the idea. That means the malware author has to know more about Windows internals than your antivirus author. And you know, that's not at all beyond the bounds of possibility. So here's a few of them. NT query system information, information file, query keys and such. These give you far more information than any available Windows 32 calls. They are the low-level utilities that are actually used by the DIL that they want you to use. You can return from an exception, so you can cause an exception and then return from it and end up somewhere else, and this will confuse the poor analyst. It will not be as simple as a call or a jump. We'll see this in the malware samples. There's quite a few tricks to move to another place and confuse people. All right. And I got a few cahoots about that. So, user account more powerful than the administrator. Well, a lot of people got it right. That's encouraging. So, the service that loads ring 0 code. All right, that's kernel driver. All right, and the native API. NTDIL, good. And if you divide by 0, what happens? That's, you go to the structured exception handler. All right. I was going to show you a project, but I think I'll just let it wait till next time, because we're going to talk more about kernel debugging next time. No class next week. In 2 weeks, we'll talk about kernel debugging. And as I said, it's really very nice now. It is so much easier than it used to be. And I'll go through this next time, but you see down here, we're going to do it in 14 and 15. We're going to do some kernel debugging, which is very easy now. You can see the kernel. It is really not that big. It is not that complicated. If you get over freaking out when you see assembly, it's not that hard to understand, and you can see it's really not at all insanely difficult for people to do things like figure out what's an NTDIL without Microsoft telling you. Anyway, I got another chat message coming in. Let's see. Class next. There is no class next week. Next week is some kind of holiday around here, and so it'll be 2 weeks before you have this class again.
So
Yep.
oh, got it.
Yeah, so up here we are 10.9, so nothing on 10.16. Next class is 10.23. And all right. So I guess that's it. I'll just clean up and go to the lab and help anybody who wants to work up there.